All right, good morning, everybody. Before we say anything more about resonance and conjugation and vision, I realized I forgot something that's decently important about oxidation. This is something you're going to encounter a lot in biochemistry, and some of you, depending on what biology classes you've taken so far, may have heard about this. Nature has several reducing and oxidizing agents, but we'll talk today about NAD+, and then its reduced form, NADH, which you may have heard of. I'm going to draw the structure of it for you. Naturally, you will want to know, will I have to have that structure memorized for the test? And the answer is no. Nevertheless, you should not just dismiss this, because there's some important principles here. So what I'm drawing for you now, NAD+ stands for nicotinamide adenine dinucleotide. So what I'm drawing for you now is the dinucleotide part. This is a phospho and hydride connection. It should look vaguely like, if you've ever seen the structure of DNA before, it should look similar to that. The dinucleotide has to do with the fact that I have two of these sugar phosphate units linked together. If sugar and phosphate don't mean anything to you, that's okay. This is a 5-membered ring sugar called ribose that you'll learn about in 352, and this is a phosphoanhydride linkage between the two sugars. And then at each of these carbons on the 5-membered ring sugars, you're going to have a different functional group. On the one on the bottom, you're going to have the adenine base that's present in DNA and RNA. At some point in your life, somebody's likely going to want you to memorize what this adenine-based structure looks like. That'll be me if you take 352 from me, but you don't need to worry about it right now. I'm just drawing it here for completeness. So that's the adenine portion, and then, as I said, NAD+ stands for nicotinamide adenine dinucleotide. This portion's the dinucleotide portion. This is the adenine portion. The nicotinamide is here, and it's a 6-membered ring containing nitrogen. Double bonds all the way around with a positive formal charge on nitrogen, and then you've got an amide group coming off that ring. So that's nature's biological oxidation agent. There's a couple others, but that's one of the major ones. If it's an oxidation agent, that means it should be able to, if we've defined oxidation in OChem as loss of electrons and or loss of CH bonds, then you would expect this reagent to be able to accept electrons or accept H-. And this is exactly what it does. So fortunately, we're going to stop drawing all of the molecule and just focus in on the business end of the molecule, which is this 6-membered ring containing nitrogen that has a positive formal charge. So I'm just going to draw that like this. And I'm going to point out that through resonance, you should be able to see that the positive charge on the nitrogen can actually be delocalized to a couple of different places, but one of the ways we can convert one resonance structure to the other would be to move the pi electrons from the bond between carbon and nitrogen over onto the nitrogen as a lone pair. And then we could stop there and leave a positive charge on this carbon, or we could move this pi bond down to form a pi bond between, I'll call it carbons 1 and 2. I don't know. In any case, the reason I've done that, you might ask, why didn't I just leave a positive charge on carbon 2? The reason for that is that it's actually carbon 4 that's electron poor, and it's carbon 4 that does the receiving of electron density. One of the other things that makes carbon-4 electron poor is this group here, though we don't need to worry about those details at the moment. Okay, so if you accept that this portion of the NAD plus molecule has a positive formal charge at that carbon, at carbon-4, and that it is electron poor at carbon-4, then what I'm about to show you will make a little bit of sense. It may help you, by the way, to draw in a hydrogen that's implied but was not originally shown. That's a trigonal planar carbon. All right, so that's NAD plus. What it can do is oxidation chemistry. So there's an enzyme called liver alcohol dehydrogenase, and this is an enzyme in your liver that takes alcohols and oxidizes them. It's part of alcohol metabolism, and the function of alcohol, liver alcohol dehydrogenase, is related to hangover. So here is ethanol, and here is how your body gets rid of ethanol. And I want you to compare this to what you saw earlier for the PCC reduction, or the PCC oxidation of an alcohol to an aldehyde. In PCC, we put a good leaving group on the oxygen. Then we did an elimination where we remove a proton attached to the beta carbon. Electrons kick down to form the new pi bond, and then the electrons from the oxygen leave with the chromium. It turns out the enzyme is going to use sort of a backwards mechanism for that. For the enzyme, the leaving group is going to be in the mechanism catalyzed by liver alcohol dehydrogenase, the leaving group is actually going to be H minus. Not a good leaving group actually, but it's going to be handed off directly to the NAD plus reagent that's sitting right by that alcohol. So it's never alone on its own, it's directly handed off. But if you think of that H minus as a leaving group, this is the alpha carbon, the beta atom is the oxygen, and you have a beta proton. So the enzyme, a side chain from the enzyme, will remove the beta proton. Electrons will kick down to form the new pi bond, and H minus will get delivered to carbon-4. So maybe I'll move the 4 out of the way. There we go. H minus will get delivered to carbon-4. This is just for reference, for comparison's sake. Product of that is your aldehyde. And then what we have over here, where we used to have NADH, where we used to have NAD plus, we now have NADH. In other words, one of these two protons that's now attached to carbon-4, what we've called carbon-4 of the nicotinamide group, came as H minus from the aldehyde. So, and if you're following through what's been going on, before we had NAD plus, now we have NADH. This NAD plus was reduced to become NADH, whereas the alcohol was oxidized to become the aldehyde. So biology does this all the time. And when you learn in 352 and in biochemistry about glycolysis and the citric acid cycle, you'll see plenty of oxidation steps, and they all follow this same basic mechanism. The unusual thing here is, of course, the hydride is the leaving group, but as I said, H minus doesn't go floating off in solution and wander around. It is directly handed off to NAD plus, and that's what makes the reaction happen. Okay. Any questions about that? So there's a section on that in your text. It's worth reviewing. It's worth making sure you can look at this and tell what's been oxidized and what's been reduced, but that's how nature does oxidation reduction chemistry. All right, back on the concept of resonance and conjugation. I wanted to jump to vision last time, but I think we should back up a little bit and just review a little bit about resonance. I want to demonstrate a point. I think you guys know that resonance means that you have multiple Lewis structures that describe the same molecule. By now, some of you have faced questions on the exam multiple times about where the negative charge can be because of resonance, and that's something that you should work on. You have the idea that if you have a positive charge or a negative charge adjacent to a pi bond, that resonance tells you where the negative charge can be. We've talked about how resonance delocalization is stabilizing, is favorable. That has to do with the fact that if you spread out wave functions through more space, their kinetic energy is lower because the slope of the wave function doesn't change as fast. But I wanted to develop this observation that resonance has another effect on how far apart the HOMO and LUMO of a conjugated molecule are from each other. So to illustrate this, we're going to draw our simplest alkene in Spartan, and then we'll get some numbers actually for the gap between HOMO and LUMO. So let's see. So we got to pay attention to these numbers on the left. Minus 7.1 electron volts for the energy of the highest occupied molecular orbital, which is the pi bond. And then let's see, for the LUMO, it's 0.41 electron volts, and that's the pi star. Hopefully that looks familiar to you, pi bond and pi star, okay? HOMO and LUMO for the alkene. And that gap between the two is whatever the difference between minus 7.1, I hate math, 7.52 electron volts. Those are units of energy. The units of energy aren't really going to matter for our discussion, but we'll just be comparing. Now let's look at the HOMO-LUMO gap for the molecule that's called 1,3-butadiene. You've got 4 carbons, pi bonds on between carbons 1 and 2, and between 3 and 4. Resonance would tell you that you could have partial double bond character between carbons 2 and 3. And you could draw another resonance structure, which I won't draw, where the negative charge would actually be on carbon 1 and the positive charge would be on carbon 4. But in any case, resonance gives you a picture that these 2 pi bonds are not independent of each other, but are actually part of the same system. And I will draw 1,3-butadiene in Spartan, and then we'll look at what that does to the orbitals. So here's the other pi bond. All right, so first off, you can see just by looking at the Lewis structure, 1,3-butadiene is flat. Okay, and if you can imagine on each of those carbons, 1 on the left to 4 on the right, each of them should have a p orbital that's orthogonal to the plane of the sigma bond. So the p orbitals on carbons 1 through 4 should be coming out towards you, one lobe out towards you and another lobe out in the back. Although if we look at it from this perspective, they'd be going up towards the top of the page and down. Is that? My mom always asks, am I cutting and you're not bleeding? Which is kind of gross, but in any case, that's a way of asking, are you getting it? You envision it? So let's look at, not that, yes. So this is the lowest energy pi orbital that you get from lining up with the p orbitals on carbons 1, 2, 3, and 4, all with the same wave function sign. Okay? We could draw that schematically by looking down at 1,3-butadiene with all the sigma bonds in the plane of the page. This is sort of our overhead view. And we get that orbital that I just showed you. Here I'm using circles to represent the top lobe of each of these p orbitals on each of these carbons. And then the smaller circle in the back represents the lobe that's below the plane of the page. I guess I can use the colors of Spartan, red and blue. Yeah, so from our perspective here, the red lobe is above the plane of the page. The blue lobe is below the plane of the page. We could, schematically, this just shows that you get this single pi molecular orbital from overlap of p orbitals on carbons 1 through 4, all with the same wave function sign. Though, as you've seen the drawing in Spartan, the actual orbital doesn't look like 4 p orbitals side by side. What it looks like is an extended orbital over the whole molecule, meaning that a pair of electrons in that orbital would be delocalized over the whole molecule, stretching all the way from carbon 1 to carbon 4. All right? Sort of got that? Okay, so then if we look at some of these others, the highest occupied molecular orbital, so this one would be filled, but it's not the highest occupied molecular orbital. The next one looks like this and has a node in between carbons 2 and 3. Okay? If we were to draw this sort of over in notability, we could start with this drawing. All we'd have to do, though, is switch the wave function sign in between carbons 2 and 3. So we'll have for carbon 2, for carbons 2 and 1, let's have the blue lobe be on top and the red lobe be on the bottom. Are you guys okay if I just continue to draw it this way? This is sort of easier to do, but you're going to have to imagine what it actually looks like, which is that. Got it? Okay. So that's the highest occupied molecular orbital in the molecule. I'll help you figure out why that has to be true, but let's continue onward. The next highest orbital is this one. This now has 2 nodes. Notice that the nodes are between carbons 1 and 2 and between carbons 2 and 3, but that you do have side-by-side overlap without a change in wave function sign between 2 and 3. So the nodes are between 1 and 2, between 3 and 4. I think I said that wrong the first time. If we were to draw that over here, actually, we'll just do that for this one. That's going to look like this. We'll put nodes. Oops. My eraser is not precise enough. There we go. So we'll put nodes in between carbons 1 and 2 and between carbons 3 and 4. So you can sort of see a pattern here: 0 nodes, 1 node, 2 nodes. We've gone through some of this before in our earlier discussion of MO theory. And then you could imagine that the highest energy orbital we would get, it would have 3 nodes in it, and to do this we'll need to erase this one. Oops. Not that one. There we go. So for this highest energy one, there's going to be a change in wave function sign between each of the carbons. And over in Spartan, that's this one. Okay? All right. So those are the 4 orbitals that you get when you mix the 4 p orbitals together on adjacent carbons 1, 2, 3, and 4 in 1,3-butadiene. The idea here is that we're not dealing with just 2 isolated pi bonds, but we're dealing with 4 p orbitals all lined up together. And this is what conjugation means. When you hear the term conjugation, it's a term related to resonance, but conjugation is when you have adjacent p orbitals that are all aligned with each other. And that makes an extended system of pi-type molecular orbitals where the number of p orbitals that you mix together equals the same number of pi molecular orbitals that you get out. All right, so the fact, all of these points are important. The fact that the p orbitals have to be adjacent to each other is important. The fact that they have to line up with each other is important. For example, if we put an sp2 3 hybridized carbon in between the 2 double bonds, that's no longer conjugated. Now you just have 2 isolated pi bonds, and the reason for that is the carbon in the middle doesn't have a p orbital, right? So that's not, yeah.
So is it a good rule of thumb that the more conjugation there is, the lower energy?
The more conjugation is, the resonance is stabilizing, and so electrons that are involved in conjugation are lower in energy than they would be in isolated pi bonds. Yes. Yep. By known and measurable numbers. So 1,3-butadiene would be more stable than the double bonds. These double bonds would be more reactive than in 1,3-butadiene, as an example. Yeah. Okay. The idea of the pi bonds or the p orbitals have to be able to line up with each other in order to be conjugated. To illustrate that point, I'll show you the following molecule. This molecule is called allene, and it's got 2 pi bonds in it, but those 2 pi bonds are not conjugated with each other, even though they're adjacent to each other. And the reason for this is that the pi bond on, we'll call this carbon 1, 2, and 3, the pi bond between 1 and 2, if you look at carbons 1 and 2, the CH bonds on carbon 1 are all in the plane of the page, as is this carbon, which means that the pi bond between carbons 1 and 2 must be above the plane of the page and below the plane of the page, like this. Carbon 2 is sp hybridized. It's involved in a pi bond with carbon 3, but the p orbital from carbon 2, the only p orbital from carbon 2 that can be involved in the pi bond with carbon 3 is the one that's in this direction, entirely within the plane of the page, like that. Those 2 pi bonds are perpendicular to each other, and orbitals that are perpendicular to each other do not interact. So allene is not conjugated. Not sure what the period there is for. Not conjugated. And that's a general principle that orbitals, and we saw this before too with actually making a pi bond. You remember we learned that you can't rotate around pi bonds because that breaks the alignment between the p orbitals. Same thing with conjugation. And you would predict as a result here that rotation should be somewhat restricted and slower about this bond between carbons 2 and 3. And it is. Rotation is slower there because you temporarily have to break conjugation to get there. All right. So conjugation involves p orbitals on adjacent atoms that can line up with each other, and conjugation is stabilizing. Now, I still want to get back to this issue of the gap in energy between HOMO and LUMO. To decide which of these pi orbitals is HOMO versus LUMO, you basically have to just account for the electrons that are involved in resonance. So for 1,3-butadiene, I see that I have 2 electrons in the pi bond between 1 and 2, and 2 electrons in the pi bond between 3 and 4. That's 4 electrons that I can use to fill these pi molecular orbitals. We can call them pi 1, pi 2, pi 3, and pi 4. And if I'm using the available electrons, I'd see that pi 1 and pi 2 are full. Pi 3 and pi 4 are empty, which makes pi 2 the HOMO and pi 3 the LUMO. I think that should mostly be review. I think we did things like that in our earlier chapters on MO theory. Now, let's go look at the orbital energies. For the HOMO, let's see, I'm trying to zoom in on that number. I have to turn my head to the side. Minus 6.1 electron volts. By the way, take a look at this, the one, before we worry about the HOMO. You guys asked if conjugation is stabilizing. Remember that the energy of the electrons in an isolated pi bond is minus 7.1. Okay? Over here for the ethylene molecule. Now let's look at the energy for the electrons in the lowest energy fully conjugated orbital, minus 8.6. So that's this stabilizing effect of conjugation. The electrons that are spread out over more atoms, they get to experience more nuclei, they get to take up more space. That's favorable from a kinetic energy point of view and a potential energy point of view. In any case, the number we want to remember for the HOMO is minus 6.1. Minus 6.11 electron volts, and then let's check the LUMO. Hopefully this will be worth it. Minus 0.71. So the gap between HOMO and LUMO here is, I'm actually going to get out my calculator unless some of you can do it in your head faster. I hate arithmetic. Thank you. Plus 5 point something. 4? Yes, thank you. All right, so just qualitatively compare the numbers. Well, hold on. Do you realize what I just said? I just said qualitatively compare the numbers. That is the definition of being quantitative. Don't let me get away with that, all right? So the HOMO-LUMO gap for ethylene is plus 7.52. The HOMO-LUMO gap for 1,3-butadiene is almost more than 2 electron volts narrower. Okay? We'll see this as general. We could do this for other conjugated systems. I don't think we want to take the time. I mean, maybe I sort of do, but we're probably going to run out of it. If we added another double bond, let's see if we even have it here. Oh, we do. Okay. Let's look at the HOMO-LUMO gap. We won't write it down, but minus 5.57 to minus 1.3. 5.57 minus 1.3. Okay, the HOMO-LUMO gap for 1,3,5 hexatriene is now 4.3 instead of 5.4. The idea is the more pi bonds we put in conjugation, the narrower the HOMO-LUMO gap is. All right, Why do we care about that, other than it's an observation? Are we just making observations today? Well, it's the difference between it's the HOMO-LUMO gap that determines the frequency of light that is required for a photon to promote an electron from HOMO to LUMO. Okay? Or if you prefer to think in wavelength, we'll do that. So if we narrow the gap between HOMO and LUMO, that means we can use lower frequency light or longer wavelength light to excite molecules, excite an electron from HOMO to LUMO. Now, you've probably wondered in the past, why are molecules colorful? And the answer is they absorb photons. Molecules that absorb photons in one region of the spectrum will be different colors than molecules that absorb photons in another region of the spectrum. Of course, molecules that are colorful are so because they absorb photons in the visible region of the spectrum. I'll tell you that the energy gap here, and even for 1,3-butadiene, is such that these molecules are not colorful. They're transparent to visible light. They absorb in the UV. But if you get enough conjugation, you can start to have molecules that will absorb in the visible region. And so there's a whole class of molecules, highly conjugated, that are colorful. And in 350, if you take 352 for me, I'll tell you a story about conjugated molecules and the dye industry that led to chemotherapy and all of this cool stuff. But for now, I'll just show you a conjugated molecule that has not just two pi bonds conjugated to each other, but much more. So this is the story of Vision, not Vision from Marvel, but your Vision. So we'll just zoom in on this molecule that's highly conjugated. It's called 11-cis-retinal. You have 12 atoms in the pi system, so 12 pi molecular orbitals. And I did the math, looked it up in Spartan. I didn't take the time to do that here, but have done it previously. That's what the LUMO of 11-cis-retinal looks like. And the gap between HOMO and LUMO is now almost 3 electron volts. And if you figure out what kind of photon you can absorb to promote an electron from HOMO to LUMO, it's in the visible region. You can look up sort of what color 425 nanometers absorbance is. I think it's in the sort of bluish, purplish end of the spectrum. I could be wrong on that. I just don't know off the top of my head. Anyway, the idea is that this molecule absorbs visible light. Now, why does that matter for you? Well, this molecule is appended to a side chain within your protein. So you'll learn about this chemistry in 352. Here's an aldehyde. By the way, some of you have probably heard of retinol. That's the alcohol form of this molecule. And has different properties. But in any case, this is the aldehyde. The oxidized form of retinol is retinal. And it gets attached to a nitrogen side chain on the protein rhodopsin. This bond is an imine. Stay tuned. You're going to learn about that in chapters 14 and 15, I think, of 352. So this molecule gets attached to the inside of a protein called rhodopsin, which is now packed into the outer segments of your rods and cones. This does the absorbing of light. What ends up happening is that when you absorb light, you excite an electron from HOMO to LUMO. Populating an antibonding orbital should weaken, even with one electron, should weaken a bond. And it turns out that as you're used to expecting, the cis configuration of this double bond is not as stable as the trans configuration. So this retinal molecule is spring-loaded and ready to change, but you have to promote an electron from HOMO to LUMO before the system has enough energy for that to happen. You promote an electron from HOMO to LUMO, you weaken one of the pi bonds, then you can rotate and get the trans isomer. It's called photoisomerization. If you zoom in on the protein, you can sort of see the way they've drawn our retinal has a kink in the backbone chain of it. That's going to straighten out. The attachment point to the protein is here. That's going to cause this end of the retinal to swing upward. It's going to bump some stuff out of the way in the protein, and this is a membrane protein, and rearranging things will actually allow ions to flow through. And when ions flow through across a membrane, you get a membrane potential depolarization, which gets translated into a nerve signal. Okay? So it's funny because while I was muddling my way through that explanation, your rod and cone cells have just been absorbing photons without any trouble. No explanation necessary. It turns out, this is really interesting, once the retinal has isomerized, the rhodopsin molecule is no longer useful. It actually has to be transported somewhere, processed. An enzyme clips out the trans retinal and then puts in a new 11 cis retinal and then traffics it back into the rod and cone cells. That takes some time. And so if you've ever stared at a light for a long time and then seen an after image, this is related to the fact that you've just exhausted the rod and cone cells in that particular part of your retina. They need a little bit of time to catch up and reload their 11 cis retinal. Okay, so you can learn more about that in neuroscience and physiology and stuff, but there's HOMO, LUMO, OCHEM going on there, and don't let anybody ever tell you any different. You may be attending parties tonight in which you want to impress people. I dare you to bust this one out and see what you get, okay? Yes?
How do we know how many high energy levels there will be? How do you know how many nodes there will be?
For molecules that are highly conjugated, how do you know how many nodes they're going to be? For HOMO versus LUMO, there's answers to this, but maybe beyond the scope of the class. Trying to think what's the most useful thing to tell you. If the maximum number of nodes you can have is one less than the number of atoms that are involved in the pi system. So notice for 1,3-butadiene you have 4 pi orbitals, but the maximum nodes you can have is 3. So that's one point. The other thing is that you go from one orbital to the other, you always increase the number of nodes by 1. At best, I will want you to be able to look at drawings of pi orbitals. You identify the nodes, then you order them in energy and figure out which one's HOMO or LUMO. You've seen questions like that before. If you're asking, hold on, that orbital looks a little bit weird, and there are nodes in places that I didn't expect, there's a couple of reasons for that. One of them is that the molecule is large. The other is that the molecule is not completely flat. And so all the rules I've been teaching you for nodes and HOMO and LUMO really apply for perfectly flat molecules. As molecules get linear molecules that are conjugated, you get beyond a certain point, and the stabilization you get from conjugation isn't enough to keep it totally flat. That's why you'll see in 352, as we talk about dye molecules, a lot of molecules that are colorful don't actually have long linear conjugated chains. The conjugated systems are rings, and that holds things pretty rigid. But yeah, kind of a non-answer to your question. It's a good question, but I don't know. Okay, what else? All right, well, so I want you to remember the pi 2 and pi 3 orbitals of 1,3-butadiene. And I want you to remember also, which we didn't necessarily have space for, what the pi and the pi star look like for the alkene. Because that's going to help you understand what's going on in a really cool reaction that was discovered in the 1920s, so nearly 100 years ago. For completeness, I'll just slide this over and I'll draw really quickly for you a pi orbital and a pi star. Oops. And because I'm hurrying, I'm just drawing the top lobe of the pi and the pi star. Okay. What can we erase here? It's good. So the reaction that I'm going to show you was discovered by German chemists Otto Diels and Kurt Alder. And in 1928, that may have been the date of the Nobel Prize, maybe not the date of the discovery of the reaction. But one of their discoveries was the following reaction. That is called cyclopentadiene. It's like 1,3-butadiene, only you forced the two double bonds to be sort of close to each other. The way I've drawn 1,3-butadiene before was like this. And there are some really great reasons to expect that it would be sterically problematic to have 1,3-butadiene be in this conformation versus this conformation, because hydrogens on carbons 1 and 4 start to bump into each other. By the way, I told you that rotation around the bond between 2 and 3 was somewhat restricted because of resonance or conjugation, and it is. Nevertheless, it's possible. People distinguish these two conformations of 1,3-butadiene by calling the one on the bottom S-trans. It's not really trans because there's not a full pi bond between carbons 2 and 3. The S refers to sigma, so it's trans-ish about a sigma bond. They call this the S-cis conformation. Those aren't stereoisomers, those are two different conformations, but that's how we talk about them. It's rotation around the bond between 2 and 3, and again, rotation around the bond between 2 and 3 is somewhat restricted because doing so breaks the conjugation. Cyclopentadiene is forced to be in the S-cis conformation because carbons 1 and 4 of the diene are necessarily tied together with that fifth carbon. So that was one of their reactive partners. And the next one, this is going to be like from your nightmares because there's so many rings. And guess what? We're going to make even more. This is their other reactive partner. And we're going to focus in on one of those two pi bonds. So the Diels-Alder reaction involves this portion, the 4 carbons of the diene, and then it involves these 2 purple carbons of what we're going to call the dienophile. That's dumb, isn't it? But that's the language people use to talk about the Diels-Alder reaction. The diene makes sense. Rather than say the thing that reacts with the diene, or rather than say the alkene or the olefin, people will call this the dienophile. We're going to number the carbons of the diene like this, 1, 2, 3, and 4. We'll number the carbons of the dienophile 1 and 2. Notice that there's another pi bond in the molecule. That one, we might have chosen to focus on that one. They're equivalent and identical. Only one of them reacts. So anyway, I'm focusing you in on these 4 carbons because that's going to help you see what happens when the reaction happens. Diels and Alder discovered that if you bring these two molecules together and you react them with heat. So the symbol for heat in organic chemistry is the Greek letter delta. I do not know why, other than that if you use your imagination, it looks like fire. So now I'm going to draw the product of the reaction, and I'm going to try to highlight the bonds that were formed in the process. Here are the 4 original atoms of the diene. 1, 2, 3, and 4. Here are 2 new sigma bonds between carbons 4 and 1 of the diene, and between carbons 2 and 1, respectively, of the olefin or the dienophile. Okay, so here are your 2 carbons from the olefin or the dienophile. Here are the 4 carbons from the diene. Also is a new pi bond between carbons 2 and 3. And then let's see, the only other thing we're missing is we still need this carbon that's attached to both carbons 1 and 4. We're going to show that as a wedge here. And then we still need to show the 2 hydrogens that were implied on purple carbons 1 and 4 and figure out where they ended up. So I think from our perspective here, it's probably best to do the hydrogens as wedges and then maybe these 2 bonds as dashes. Okay, that's one of the 2 stereoisomers that you observe. The other stereoisomer that you observe is where the hydrogens are dashes and the carbons are the wedges. Okay, so those were the 2 products that they found. And it was one of the reasons this is a Nobel Prize winning reaction is just the major increase in complexity you get when you do this reaction. 2 fairly complicated products to begin with, but then you make a much more complicated structure. So let's talk about what's going on when you make this reaction. When the reaction occurs, you make a new sigma bond between carbon 4 of the diene and 1 of the dienophile. I guess we can use color 4 and 1. Whoops. Let me try that again. You make a new bond between carbon 1 of the diene and carbon 1 of the dienophile. You make a new sigma bond between carbon 4 of the diene and then carbon 2 of the dienophile. And you make a new pi bond between carbon 2 of the diene and carbon 3 of the dienophile. Let's look at what we lose. We lose the pi bond between carbons 3 and 4 of the diene. We lose the pi bond between carbons 1 and 2 of the diene. And we lose the pi bond between carbons 1 and 2 of the dienophile. So, based on that, make a prediction. Yeah, sorry, go ahead. The pi bond on the far right should have stayed there. Thank you. I was in a hurry and just forgot, so thanks for that. Sorry about that. So, with that in mind, make a prediction based on what you know about the stability of pi bonds versus sigma bonds. Is this reaction uphill or downhill in energy? Pi bonds are more or less stable than sigma bonds? Less, because they hold electrons farther from the nucleus and because they go through a node, right? So their kinetic energy is higher. So if you trade 3 pi bonds for 2 sigma bonds and a pi bond, this is downhill in energy and it is exothermic. Okay, we'll have more to say about this. There's some fun stereochemical issues, there's some fun synthesis issues to deal with, and we still need to talk about HOMO and LUMO. So we'll do that on Monday. In the meantime, have a good weekend.